All right, we're going to be doing some more graphing with complex and rational numbers. You will need something to write down some notes on this. I'm going to be giving you more information than we had, but you definitely will want to take notes and write these down. All right, we're going to do some more graphing. First of all, last week we went over asymptotes, and we're going to review what we know about asymptotes and then expand that further because there are more ways or more things we can talk about with asymptotes. And we're also going to talk about, you'll need to learn some extra stuff. You're going to learn how to find something called discontinuity and find some holes in the graph. And those are two new things. So we're going to expand our knowledge on asymptotes. We're going to find continuity and holes today on our graphs. All right. You already know that in asymptotes are boundary lines that a rational function approaches but never crosses. And when we did that, we did dashed lines on our graphs to show them so that we can put our graphs in there. That we already have done. Well, there are 3 types of asymptotes, and you have already done the horizontal and vertical, and we're going to expand that horizontal and vertical, and there are also some diagonal or slanted ones, but today we are not covering the slanted ones. So what we're going to do is we're going to only cover these vertical and horizontal ones. Now that horizontal asymptotes, there's a little parenthetical phrase there that says the graph can cross these. So it sounds like it's kind of a little bit different when we set up here that the asymptotes never get crossed. Your horizontal asymptotes, you're going to have multiple parts of this graph, and some of your graphs will cross them, but other ones will not. So there are going to be times when those horizontal asymptotes, one part of your graphs will get close to it, but other parts will cross them. All right, but we will not be doing the slanted ones. I just want you to know that there are slanted asymptotes, but we won't talk about them in class. All right, let's talk about the vertical asymptotes. The vertical asymptotes exist where the denominator would be 0. This is actually the most straightforward one. You have saw that last week. It's where the denominator will be 0, and so they can be moved up and down based on those shifts, and you did move those. But today, we won't have as many shifts. We will just have where the denominator is equal 0. We're going to continue to draw those dashed vertical lines. And there can be more than one of these vertical asymptotes. Last week, we had one vertical asymptote and we were done. This week, we will have multiple of them depending on how the graph, or what kind of a polynomial is in the denominator of that fraction. Okay? You might have some that we will factor, and you could have 2 places where it crosses, where it equals 0. So we might have more than one. All right, what we're going to do, the way we're going to find them is we're going to set the denominator equal to 0 and solve for x. There will be times, though, where you might have to factor when we're doing that. All right, now we're going to do the horizontal asymptotes. I'm going to let you know that these are a little more complicated. So you're going to need to make sure that you write this stuff down. You might not completely understand it till we actually go ahead and do it, though.
Do we need to write down that part?
You can. When I talk about the numerator, I'm talking about the entire top of the function. And when I'm talking about the denominator, I'm talking about the entire bottom of that, okay? So if you don't remember which one's numerator and denominator, you might want to write that down, okay? All right. So we already know this part. This is our review part. The horizontal asymptotes are also dashed lines drawn horizontally to represent another boundary line. We did that one before. Last time it was always on the x-axis, and it moved up and down based on the shifts. But now we're going to use this. We're going to find the horizontal asymptote by comparing the degree of the numerator with the degree of the denominator. So before we even start, we need to even remember what that word degree means. So if I give you x squared plus 5x plus 4, what's the degree of this? 2. How did you get, that's correct, Isaac. How did you get 2?
Because it's got a 2 on the x.
Yes, it's got the highest exponent is a 2. So we need to remember the degree. And so we're going to compare the degree of the numerator with the denominator, okay? So I'm going to abbreviate numerator as n and d as denominator. So here's something that's already in a shorthand notation. The h here, HA, stands for horizontal asymptote. So if the degree of the numerator is less than the degree of the denominator, then y equals 0 is your horizontal asymptote. If the degree of the numerator is greater than the degree of the denominator, then the graph has no horizontal asymptote. All right, we've done numerator less than denominator and numerator greater than denominator. What other option do I have?
Equal to?
Equal to. So this is the last one. If the degree of the numerator equals the degree of the denominator, then we do something special with this. I'm going to let you write that down and then I'll explain it to you. You will need that fraction down here. You will, and I'll just dissect that for us, okay?
So we need to write that up.
This means the leading coefficient of the numerator. That's what that means. And this means leading coefficient of the denominator. Let me do one, okay? So if I had x squared plus 2x over, let's do a 3. And then I had 2x squared plus 5. What's the degree of the numerator on this one?
2.
Yes. What's the degree of the denominator?
2.
2. So I want you to notice that it falls under this category. They have their degrees are equal. And so now we look at what's called the leading coefficient. On the top or the numerator, what's the leading coefficient? What is a leading coefficient? Natalie says 3. She is correct. The leading coefficient is the number in front of the one with the degree. That is 3. What's the leading coefficient of the denominator?
2.
2. So our horizontal asymptote is at y equals 3 over 2. Okay? So if the degrees are equal, then I just take the leading coefficient of the numerator and divide it by the denominator. That is what this piece over here means. That's what that means.
LC means leading coefficient.
That's correct. And the little n down the bottom means of the numerator. And then this means leading coefficient of the denominator. Now we got to figure out what holes are. A hole exists when the same factor exists in both the numerator and the denominator of a rational expression, and the factor is eliminated when you reduce. I would suggest that you do not write that whole thing. When I say whole, the whole thing. Let's actually show you what it is, okay?
So don't write this down yet?
So don't write this down yet. If I had a function that looked like this, is there, and then up here in our definition it says, it exists when the same factor in both the numerator and denominator of a rational, is there a factor that's in both of them? Which one?
X plus 4.
The x plus 4. So what can I do with that x plus 4? I can cancel them out. So there will be a hole at the x plus 4. So there is a hole at x actually equals negative 4. How did I get the negative 4?
Because you took it out and solved for X.
That's right. I said that part equal to 0 and solve for x. So I'm going to pause the video right here and let you somehow summarize what a hole is. If you don't want to write that whole thing or you want to write just my equation part, but summarize what a hole is without having to write that whole sentence there. So we got holes, and now we're going to talk about some other things, some things called discontinuity. And so the domain at this part, then we're going to go to discontinuity. So
Mocha.
we're going to go to domain, and the domain is where, if you remember, we could have everything except where the denominator was equal to 0. And notice I'm also going to keep the pieces where they equal 0. Those are still part of the domain, which is the excluded values that you were doing last week. This is also where your vertical asymptotes are. And we're also going to talk about something called discontinuity, okay? It's not continuous, or it cannot go through those points. So it's not only is it your vertical asymptotes and your domain, but it's also a place where it is not continuous. There is, the graph does not touch those spots. So it's discontinuous at those spots also. So your domain and your discontinuity are going to be the same, except you're going to write them a little different. Why is my whole not at 2? Why is it only the part of the domain?
What we did was use the x plus 4. Is it because x plus 4 is on both sides and it's the only one you can cross out?
That is exactly right. It's because the x plus 4 was on the numerator and the denominator, and we could cancel it out. But the 2, the x minus 2, is not on the top and bottom, so we couldn't cancel. That is exactly right, Isaac. Good job. All right. All right, we did discontinuity. We talked about vertical and horizontal asymptotes. We talked about domain. Now we're going to bring it all together, and we're going to do number 1. You have number 1 there in your notes. You also will need to have your graphing calculator out in front of you, because it's actually going to help you very much to draw the graph also. But to actually find all the pieces, so I would suggest that you don't worry about the graph at first. Let's just answer the questions.
Should we simplify first?
Yes. So what we're going to do is we're going to find the points of discontinuity, the holes, the vertical asymptotes, and the domain, and then we're going to sketch it. I would do all that first and then sketch it at the end. So we're going to have to, yes, simplify this to begin with. So can I factor the numerator? Can I take something out of the top of the numerator?
Yeah.
You can divide by 2, and I'll have an x squared plus 2x.
No, x squared plus x.
I'm sorry, thank you. Minus 12, correct?
Yeah.
I'm going to
I
keep...
can factor again.
And then I can factor it, right? And we're going to do the box method on that one. I can do x and x. And what multiplies to be 12 and subtracts to be 1?
3 and 4.
3 and 4. Is the 3 going to be a negative or the 4 going to be negative?
It's a 3.
3.
Okay, so we're going to have x minus 3 and x plus 4. Okay. Now the denominator. The denominator, I don't even need to put it there, because we can just put it, we can just factor it right there, okay? We're going to have x and, we can do the box method. X and x. I heard 4 and 2. Adding them both or subtracting them both?
I'm adding them.
Adding.
Yes.
Adding both.
Okay. Is there something I can cancel out of that?
The 4s.
The 4. When you cancel it, don't make it so that we can't see it very well, because that's actually, when we cancel it, what does that become?
Our whole.
One of our holes, right? Okay, so we have discontinuity. I'm going to actually start at the top. And we have a 2x minus 3 over x plus 2. And let's start at the top with our discontinuity. You can maybe just do DIS if you want. Is x equaling what and what? That's where the denominator equals 0.
Negative 4.
Negative 4. We have to do both of them right there. Yes. Negative 4 and...
Negative 2.
Yes. I'm going to just do it in order. We just did discontinuity. Now we need holes.
Negative. Positive. Yeah, negative 4.
We said the holes were where there's something canceled out. So that was at x
negative
equals 4. Negative 4.
4.
Now we're going to do our vertical asymptotes. Is that the next thing on the list?
Yes.
So I'm going to just call that VA. Your vertical asymptote, how do we do that?
Set the denominator equal to 0.
Yes, set the denominator equal to 0.
So it's going to be negative.
All right, so our vertical asymptote is what's left. It's right here. It's that x, and we set that equal to 0, so it's going to be x equals negative 2. What about our horizontal asymptote, or HA? How did we do that one? Remember what? Back to our notes. What do we do to find our horizontal asymptotes?
Compare the degrees of the numerator and the denominator.
Yes, we compare the numerator and the denominator. So
It's just going to be 1.
all right, so we're looking at our horizontal asymptote. We compare the degrees, right? The degree of the numerator is 2. The degree of the denominator is 2, so those degrees are equal, right? I'm going to just write that for right now. You don't have, this is not part of the answer, but it'll help us. Degrees are equal.
That's right, I remember now.
And why are they equal?
Because the numerator here is a 2 as that degree, and that is a 2 for that degree.
So it's going to be 2 over 1, so it's going to be positive
So
2.
then when they're equal, what do?
We divide the leading coefficient of the numerator by the leading coefficient of the denominator.
And the leading coefficient is 2 here
2
and
over
invisible
1.
1. So it's 2 over 1
Which
or
is
just
2.
2.
So it's
So it's y equals. So it's y equals 2.
Do we have to write that degrees?
You
next
do
to
not
the
have to. I wrote that so that you'll understand how I got that. Please ask me questions, you guys, if you don't understand how I got the horizontal asymptotes. All right, what do we have left to do?
graph, right?
No, we have one more thing to find.
Oh, the domain.
The domain. The domain is x, and that's what can we put into that equation? With what x values are we allowed to put in? Everything except two numbers.
Everything except our discontinuity.
Our discontinuities, or where the denominator equals 0. So,
-2 and -4.
yes. So x cannot equal -2 or -4. Let's use all this information to graph. I'm going to first do the horizontal and vertical asymptotes, okay? So I'm going to do x equals 2. That's right. Excuse me, -2. X equals -2. And y equals +2. Okay. We know there's going to be a hole at -4. I'm going to show you what to do with that in a moment. But what I want you to do is on your calculator, you can put this whole thing right there, or your simplified version, and it should be the same thing. Except our hole will not be on the first one. So I think you can put your simplified version. I think that would be faster probably. Okay, so the graph looks like,
Oh, sorry.
here I'll show you. That's what, I don't know if I can do that. You saw on here, we're just going to go swoosh. And whereabouts does it, can I see at least where it kind of crosses the
About
x-axis?
-3.
We estimate.
That's exactly right. Do you think it crosses about 3? Is that what it looks like that?
-3.
Wow.
I don't need anything super technical. You know it's going to get really close to these asymptotes. Now, there's one thing you got to put in here though. You got to put the hole.
What's the hole?
It's where it cannot
-4.
equal. And if we have here, the hole is at -4, correct?
Well, you cross -4, not -3.
And so right here on this little part of the graph, you need to have a literal hole on the -4 line, because it can equal everything close to that -4, but not -4 itself.
What about the -4 on the other side of the graph?
Just the x. This is at an x of -4 on this line here, of an x of -4, so that's where the -4 crosses our graph. So that's why we need it at that part. We're going to move on to number 3. We're going to factor this first so that we can find our discontinuities and our holes and our vertical asymptotes. And so the numerator factors into what? We can do the box method there. X and 2 and 1. But we need it to be 3. These are going to be both negative, so I'm going to have x minus 2 and x minus 1. What about the denominator? Can I take something out of everything in the denominator? Can I take?
Yeah, you can take a 4 out.
Okay, I'm going to do it underneath for right now so I can scoot it over. I'll have x squared minus 2x minus 3. Okay? So I'm going to have a 4 right there. And what am I going to... Then when I do the box method... Let me make it bigger. When I do the box method... I'm going to have x squared, or x and x, and I'll have 3 and 1. But one of those has to be negative.
The 3 is a negative.
That's correct. So I'm going to have negative 3 and positive 1. So I'll have...
Wait.
Let's make this bigger.
Oh, so nothing cancels. Gross.
So there'll be no holes?
No, because we've got a x minus 1 on the top and an x plus 1 on the bottom, right?
Okay.
Gross.
So Ryan says we're not going to have any holes.
Right?
All right. I believe that's true. All right, what do we have? Any discontinuity?
Positive 3 and negative 1.
Yes. X equals 3 and negative 1. Next thing after discontinuity is holes.
0.
Actually, if we put 0, that would mean 0 is the hole.
So none?
So it's none. And next thing is vertical asymptotes.
So...
The vertical asymptote is, how do we find those? Do you remember?
3.
Positive 3 and negative 1.
Yes, and they're x equals because we need to have, that's an actual line. All right, so we have x equals positive 3 and negative 1. What about horizontal asymptotes?
Wait, hold up, Mom.
So we've got the vertical asymptotes is where the denominator is 0. We got the horizontal asymptote because the degrees were equal up here. And so we took the leading coefficient of 1 and 4. So it's 1/4. The next thing we need and the last thing is the domain.
Which is negative 1, 3.
No, it's 1, negative 3.
It's 3, negative 1.
Or negative 1, 3.
Oh, I see.
What is that?
And it's x cannot equal 3 and negative 1. Or if you want to say negative 1, 3, it doesn't matter. I'll move that down a little.
Negative 1, 3 and not 3, negative 1.
Because, Isaac, if you look on the denominator, we have to set them equal to x, set them equal to 0, and solve for x. And so then we would add the 3 over the other side, making it x equals positive 3, and subtract the 1 over the other side, making it x equals negative 1. Does that make sense?
So we'd have okay, so we'd have x minus 3 equals 0, and we'll move it over, right? Okay. All right, so now that we have all this, before we put it in our calculator, I am going to do my horizontal and vertical asymptotes. I want you to notice they're going to do something different than we've ever seen before. We're going to have 2 vertical asymptotes. We have one at positive 3 and one at negative 1. And we have a vertical at 1/4, which is somewhere down here.
You mean a horizontal at 1/4?
I'm sorry, horizontal at 1/4.
You got me so confused.
This graph is going to look different than we've ever seen before. It should be a positive 1/4. Yes. So now we're going to put this in our calculator. You have an option. You can put it in like the first one right here or the second one. Remember, it doesn't matter, and we didn't cancel anything out anyway. So whatever one you want, just be careful because this one over here, this one over here, you're going to have to make sure that you divide that whole denominator. Otherwise, you're going to get some strange thing. I would suggest you put this one in, but that's up to you guys.
Wait, really?
Well, because when you put the 4 times negative 3, x minus 3 and x plus 1, you got to put a parentheses like way out here also. So a graph was, first one went like that, then we went to that one, and then it went like that. And I don't need it to have any specific, we just kind of wing it like we said before. Do we have any holes on this one?
No.
No holes. So we're done. Okay? All right. Let's move on to the next thing we're supposed to do on this one. Now, I think you're going to like this next part because it's no graphing now. Okay?
What,
Let me move
Isaac?
this back now. All right. We're going to simplify some complex rational expressions. Are you ready?
Sure.
All right.
Kentucky Fried Chicken!
Now we're going to do some Kentucky Fried Chicken. We're going to do some KFC. If you remember last week, the KFC stood for keep, flip, and change. Okay?
What I said?
Yours, tell us yours again, Isaac.
Smell bad? I don't know. That's what I
Something
remember.
about...
All I remember is the dead monkey smell bad.
Oh, yeah, but you said yours something about flip that sucker and multiply.
Yeah, when dividing fractions, don't ask why. Flip that sucker and multiply.
That's what it was. When you're dividing, don't ask why. Just flip that sucker and multiply. I remember that. All right, so that's what we're going to do, and we're going to do that on number 7, okay? Let me explain how we're going to do the KFC.
What?
All right, so we're going to flip, keep, flip, and change. What I want you to notice here is this is the numerator, but it's got a fraction in it. And this one is the denominator, and it has a fraction in it. These are called complex rational expressions because they're fractions inside of fractions. Are you with me so far?
Sweet.
So we're going to keep the 4/25. We're going to flip the 1/5 because we are dividing. So we're going to change it to 5/1, and we're going to change instead of... A fraction means divide. We're not going to divide. We're going to multiply. Can I reduce that before I do it?
Yeah. The
I can-
5 and the 25.
Okay, so I can do...
So it should be 4/5.
I can take that and that. So it should be 4/5 is the answer. That is correct. Okay? Keep, flip, change. Or flip it and multiply. Or multiply by the reciprocal. Here we go. Number 9. I want you to notice that the main fraction line for this one is a little bit bigger than these little ones. So that's how you can tell what's on the numerator of the whole numerator and the denominator. So I'm going to keep the 3/4. What am I going to flip? Flip that m squared over 4.
Yeah.
So it's going to be 4 over m squared.
So it's going to be 3 all over m squared.
I can reduce these here, leaving us with 3 over m squared. It does not ask us to write our excluded values, so we're done. Number 11. Notice now it got bigger, okay? So number 11, this is the numerator, and this is the denominator. We're going to keep the numerator, x minus 1 over x minus 2. We're going to change, and we're going to flip that bottom one. The bottom one will be x minus 1 over 2. Does anything cancel?
No.
No. So we had to multiply that all out. What is x minus 1 times x minus 1?
X minus 1 squared.
That's true. I'm trying to decide. They're going to write it. They're going to multiply it all out.
Oh,
But I don't know that that's any more simplified. I think x minus 1 squared over 2x minus 2 seems more simple than multiplying it all out. So I'm going to let you keep it like this. They're going to have this. Their answer is going to look like x squared plus 2x, minus 2x plus 1 all over 2x minus 4. That's what they're going to write. Okay? I think that the first one is better. I mean, not better. I'm going to let you keep that one because I think that's just as simplified. Okay?
Okay, so I can just circle the yellow circle and be done.
That
Or
is,
the red circle.
now it's the red one. Yeah, the red, yes, that's, I'm going to tell you though, in the answer key will not have that. The answer key will have this orange circle as the answer. And I'm going to let you do the yellow circle.
Okay.
Okay. Here we go. Are we ready? This is what we did in this lesson. We added to our knowledge of graphing rational functions. We found more about asymptotes. We did wholes and discontinuity. After that, we learned how to simplify complex rational expressions by keeping the first, flipping the bottom, and changing it to multiply. I hope this has been helpful. Goodbye.